As we have discussed, the second branch of calculus comes from the discovery for the calculation for the area under a curve. Recall the topic of Riemann sums. If the graph below were broken into 5 rectangles, the area would be an under or over estimate depending on whether the LRAM, RRAM, or MRAM was used. Just a quick review of the terms LRAM and so on. LRAM is the left-hand rectangular approximation method. That's where the curve would pass through the left corner of the rectangle. RRAM is the right-hand rectangular approximation method. That's where the curve would pass through the right corner of the rectangles. And the MRAM would be the midpoint rectangular approximation method. And that's where the curve would pass through the midpoint of the rectangles. Exact area. Regardless of which rectangular approximation method is used, the summation formula would be sigma, as I goes from 1 to n, of f of c sub 1 times delta x. And recall that this summation notation would only be an approximation. So, if we wanted to calculate the exact area, what options do we have? Well, let's keep these two sayings in mind. They're almost like mantras. The more rectangles, the more accurate the area under the curve. And the other would be, in addition, the more rectangles, the smaller and smaller the width of each rectangle becomes. It's almost like you're crowding a lot of rectangles into a small space. The width of those rectangles would have to become smaller and smaller. In the topic of infinite rectangles, by finding the limit as n approaches infinity of the formula, we can find the exact area under the curve. And remember that n is the number of rectangles. If f is defined in the interval, the closed interval, from a to b, and the limit of the Riemann sum exists, then f is said to be integrable on the closed interval a to b and is denoted by this. So we take our limit of the summation notation and we introduce this new symbol called the integral sign. So the summation is equal to the integral of f of x dx as x it ranges on the closed interval a to b. Since we allow the number of rectangles to approach infinity, the width of each rectangle, or in this case delta x, would become infinitely small, almost zero. So we denote that with a dx. This is referred to as the definite integral and is read as the integral from a to b of f of x dx, or the integral from a to b of f of x with respect to x. In our notations down here, this symbol is known as the integral symbol. The lower limit of integration is a, that goes at the bottom of the integral symbol. The upper limit of integration is b, and this would be placed up here. The integrand, the function that is being integrated, is f of x, and the differential, or the infinitely small delta x, is denoted by dx. Continuing our discussion on the definite integral, let's dissect what the following integral represents. So our integral from 2 to 5 of the quantity negative 0.1 x squared plus 4x dx, where 2 and 5 would be the closed interval, a and b, like this, and f of x is highlighted in the yellow. So the integral represents the area under the curve of f of x as x goes from 2 to 5. Let's try to visualize the represented area and confirm if you're right on the next slide. The visualization of the integral would look like this. Here's our curve of f of x, and x would go from 2 to 5. And you can see our rectangles would be based on here as we go from 2 to 5, as we discussed in the previous chapter. The difference with integrals is that these rectangles would be squeezed smaller and smaller as we fit more into that space. And the more we fit in, the smaller the width would become, and the more accurate our estimate or our area calculation would be. Properties of integrals. Below are some properties of integrals, and they may look familiar to you because they're very similar to derivatives. Here's each one read out. So we have the integral of a to a of f of x dx is equal to 0. Number 2, we have the integral from a to b of f of x dx is equal to the negative of the integral b to a of f of x dx. Our third one is the integral from a to b of k times f of x dx is equal to k times the integral a to b of f of x dx. In this case, k is a constant term. Our fourth one, we have the integral of a to b of f of x plus or minus g of x dx is equal to the integral of a to b f of x dx plus or minus the integral of g of x dx. And then finally, we have the integral of a to b of f of x dx is equal to the integral of a to c of f of x dx plus the integral of c to b of f of x dx, where c is in between the endpoints a and b. We're going to discuss this more in depth as we look at each one of these properties individually. Let's break down each property into understandable language. So the first property we discussed previously was when we're integrating from a to a of f of x dx, and we say that's equal to 0. Here's why it's equal to 0. This property describes an interval beginning at some value a and ending at the very same value, a. Thus, the length of the interval would be 0. And if that's the case, the area would also be 0. In this property, notice that a and b are reversed. Here we're starting with a and ending on b. Here we're starting at b and going towards a. And what equates that is that the negative right there in the front. So this property states that the integral starting at a and ending in b is equivalent to the negative of the integral starting at b and ending at a. For this property, notice that there is a constant k multiplying the function. If we factor out that k, the result of the integral would be the same. So this property states that if a constant factor k can be factored out of the function f, you can factor the same constant out of the entire integral, and the resulting value would be the same. This property states that the integral of the sum or difference of two functions on the same interval is equivalent to the sum or difference of the integral of each function separately. So given that we are integrating two different functions, f of x and g of x, and it's either a sum or difference of those two functions, we can integrate each function separately. So we can take the integral of f of x plus or minus the integral of g of x. The next property we'll look at describes an interval from a to b with some value c in between a and b. The value of the integral from a to b is the same as the integral from a to c plus the integral from c to b. So looking at the pictures up here we have some number c that's in between a and b. And if we're starting out integrating from a to b, we can take the integral from a to c first, find that value, and then add that to the integral from c to b.